Hey guys, welcome back to Introduction to Computer Networks. This is Polly, but this time speaking from Taiwan. And we are here, week 13, episode 23. And this week, unfortunately, we have quite of assignments due. First is PA8. And we have here what's planned, 7 quizzes. But there's a chance that we might not have enough time for the last 4 quizzes this week. Okay. Now, even if we have all the 7 quizzes are straightforward. Okay. And in fact, quiz 41 to 43, these are 3 quizzes in a series that are just to prove a point. All right. So assignments, many, but should be straightforward. And the result of exam 2 will come out tomorrow at about 1 p.m., just like exam 2. Good? All right. And this time, finally, it's a better normal distribution, all right? And this is actually by design. This is not to make you feel bad, all right, guys? Did I mention that I don't judge people based on the grades? Okay? All right, good. Oh, thank you for your support. Oh, hi. Okay, good that you have passion learning more about computer networks, cellular networks. All right, good. And with that done, let's move on. Last week, what we talked about are mainly all these small topics in chapter 4.3, and what chapter 4.3 is about is IPv4. Okay. What the last section that we have not yet done with the chapter 4.3 is just this topic, IPv6. Okay, but you guys actually know a bit about IPv6 already, right? Because the last quiz that you guys went through last week was about, hey, whether you like IPv4 better or IPv6 better to address, or NAT better or IPv6 better to address the address shortage problem, isn't it? You know what? IPv6 is here not only to address the address shortage problem. There are actually a couple more other reasons. All right. So this video more formally talking about IPv6. Very brief, 1.5 minutes. You're here. The other 2 reasons we want IPv6. Last topic in 4.3, the IPv6. This is also the protocol some of these network engineers thought more legit, addressing the IP address shortage problem, instead of using these controversial netboxes. And that is why we actually upgrade from version 4 to version 6. The approach is very straightforward, expanding the 32-bit IP address space to 128 bits long. So the main goal of having IPv6 is exactly this. There are 2 secondary goals. First is to speed up the processing or forwarding of the packets as they come into a router. So in the data plane, packets coming in really fast. If we could reduce the forwarding time, processing time, we make the transmission process as efficient as possible. Okay. So you see in IPv6, the header is also changed, okay, to try to reduce the forwarding time, the processing time. The secondary purpose, this. We want to add something so that we could label the packets, so we could separate a group of packets from other, okay, and make them flows, different flows. Now, with the different flows of these packets, we could then assign priority to a specific flow versus lower priority for other flows. Okay. Therefore, okay, we could establish a more flexible levels of quality of service for these different flows. Okay. You see also header fields there to support labeling of flows, setting priority of the flows. All right, you see, we want to process these packets faster and somehow differentiate the packets for their different purposes. And we call now these packets being flows. Okay, so we have packet flows. All right. Now, the next video is finally to talk about the IPv4 packet header format. Just like we spent quite a bit of time talking about IPv6 packet format, just like we spent a lot of time talking about IPv4's packet header format. Okay, and we'll see in this video, unfortunately very long, 7.5 minutes, where you will see that the IPv4 packet header is in fact longer, in fact twice as long as IPv4. In IPv4, the packet header is only 20 bytes, but in IPv6, 40 bytes. Okay. But what's very unique in IPv4 packet header is this. Even though it's longer, but there are much fewer fields in the packet header so that it looks concise and clean. All right, so let's take a look at how the packet format is like. The IPv6 packet format. The header part of it is fixed size and 40 bytes long. Now recall version 4. Is it fixed size or variable size? It's actually variable size because of the option fields there. So that field, in case we have more options, then it's going to go longer. No fields, 0. And therefore, IPv4 header size is 20 bytes minimum and could potentially be more. Okay. Now you probably recall, right? When we were talking about the IP header size, 20 bytes, we also mentioned the TCP header, 20 more bytes. Together, 40 bytes, just to store the control information. If we're sending a real message that's 10 bytes long, the entire packet will be this long, while only 10 of them is effectively sending data. This is very low utilization. So yeah, Poly kind of promised you that in the next version of IP, we're going to reduce the size of the header. But you see here, is 40 longer or 20? Yeah, 46 in fact has a longer header. But this is necessary, and this is as small, as short as possible already. Allow me to explain. In the IP packet header, there are two fields called the source IP and the destination IP. In version 4, the IP address space is only 4 bytes long. Now, to store source and destination IP, you only need 8 bytes. But in version 6, the main goal is to expand the IP address space. So unavoidably, we have very long IP address, and two of them, one for source IPs, another one for the destination IP, together 32 bytes. If you look at this, version 6 header 40 bytes, so we have only 8 bytes for the additional fields. While in version 4, 20 bytes long, we have 12 bytes for the additional fields. So the designer of IPv6, you see, try very hard to reduce these other unnecessary part of the header, removing them away, removing these fields away from the header. Okay. So 40 here, longer indeed, but it is actually after we try very hard making the header part as compact as possible, as small as possible. In fact, the second feature of the version 4 header is this. To recall, in the fragmentation and reassembly function of IPv6, we have these 3 fields in a row. ID, fragmentation flag, and offset. This row of extra header fields remove entirely, okay? And this is done by disabling the fragmentation and reassembly function in version 4. So in IPv6, no longer allowing fragmentation. And this is why we see version 4 header, although longer, it looks really clean and compact. Okay. First, the source address. Second, destination address. And the rest is only just 6 more. 1, 2, 3, 4, 5, 6. First, here is the payload length. If you recall in version 4, we do have what? The header length and the entire packet length. Because the header size can vary. And the packet size, because the data size can also be different, so we need 2 lengths. Here now, having a fixed packet header size, we need just the payload part, okay, the payload length to indicate the size of the data down here. Hop limit, this is just the TTL field, okay, just like in IPv4. Next header, it looks odd, we've never seen this before, but this is really the upper layer field in version 4. So what it does is, once we extract the payload, we actually forward the payload to what's indicated by this pointer here. And so further processing will be done using this handler on the payload. The version field, we also have this in version 4. So the only difference is that this value will always be 6 in version 6. priority and flow label. These two are new. So flow label here is to allowing us to group a specific set of packets together. So coming from one application, coming from one service, they could be carrying flow ID 1, and other packets from other services, flow ID 2. So we could identify packets for one flow, and packets for yet another flow. So we could separate these packets traveling the internet. As a result, we could then provide different priorities to different flows. So some flows will go earlier than the others. Therefore, we provide flexible levels of these QoS. Now, there are some more fields we remove, not just the fragmentation fields. The header checksum in IPv4 header, that is removed because to calculate checksum takes time. To check the checksum takes also time. So let's try to reduce the forwarding processing time as much as we can. So let's remove the checksum part. And take the risk of some bits in the header being flipped. We might have some, might run into some errors, but chance is very low. We way higher here, way more here, trying to make sure the forwarding part is fast. And we move the option part down to the payload so that when we grab the payload and give it to the handler is going to look at the first few lines in the payload, and those will contain the options. There's one more thing. ICMP version 6. What is ICMP? You need to think back. In one of the earlier overview slides, I was talking about the functions and protocols implemented in the network layer. In the data plane, we have forwarding. In the control plane, we have routing and management. ICMP is one of these protocols implementing the management function. So we also extend the version for ICMP to version 6. And the reason we need the version 6 ICMP is so that we could send a special message, packet too big. Allow me to elaborate. Now we don't have fragmentation and reassembly. But the fact that some of the links on the internet allows smaller MTU is still there. So what if we have big datagram coming to a router and the next link is saying MTU smaller? But we cannot fragment this datagram anymore. What should the router do? What can the router do? So the mechanism in version 6 is to send a special message, an ICMP version 6 message, back to the data source saying packet too big and the better packet size is below this MTU value. So there's additional message being defined in ICMP version 6, allowing the routers to manage themselves, deciding what is the best datagram size. And we'll just ignore this part. Multicast, we'll just not talk about it at all. It's a can of worms. So this is IPv6 packet format. All right, so next video is about this. So the routers nowadays, some of them still run IPv4, some of them begin to run IPv6. But the thing is that now you see in IPv6, the destination address is 128-bit long, right? How do you send to an IPv4 address host? And how do you send from one IPv6 host to another IPv6 host where you have IPv4 routers in between? So this is an issue. We'll talk about adoption of IPv6 later, but next video is going to tell you a special technique we use such that we can manage backward compatibility. So even though we're sending data from a native IPv6, but we can send it through IPv4 networks in the middle and reach the other IPv6 destination hosts, all right. And that technique is called tunneling. So this is a technique that's very often used to maintain backward compatibility in a distributed system. This video, a little bit long, 6 minutes, and you'll find it interesting. So this topic is a little bit special, We will be talking about how we move from an IPv4 internet to a IPv6 internet. You see, there's no way we turn down all the routers in the world and upgrade to version 6 simultaneously and turn them back on and hope that they will just work. No way. It's really, really risky. And hey, we are all, right, living in different time zones. What do you mean by having a flag day? And not to mention that turning the entire net down for an entire day, okay, and wait until all the debugging and upgrading is done. Well, yeah, some part of the world might panic. So how will the network operate with part of the internet running IPv4 and some other parts running IPv6? So transition from IPv4 to IPv6, this is what we meant to talk about. How do we allow the mix of IPv4 router to IPv6 routers? And the technique, okay, let me tell you ahead of time, is called tunneling, okay? Establishing tunnels, okay, between routers, okay, at the edge of the IPv6 network to IPv4 and then back to IPv6. And the technique is working this way. So if there's a packet generated from the IPv6 space, so then the network layer in the machine in the IPv6 space will be generating an IPv6 packet. Okay. Once it hits this border between IPv6 and IPv4, this router standing at the border will be implementing both IPv4 and 6. Okay. So this router will also be doing this. Okay. Take the IPv4 packet generated from the take the IPv6 packet generated in the IPv6 space and encapsulate that into an IPv4 packet. Okay, so this is the IPv4 packet, okay, and this is the original IPv6 packet, okay, generated from the IPv6 space. So that IPv4 packet is encapsulated, so being contained, okay, in this bigger IPv4 packet. All right. So you see here, we'll have packet header fields here, source IP address, destination IP address, and etc. etc. Now IPv4 packet here coming from the border of IPv4 and IPv6 connection is going to travel the IPv4 network fine because the header fields interpretable by the routers in the IPv4 space, and eventually reaching the other end, okay, the other border between IPv6 and IPv4, and that border router there would extract, okay, the IPv6 packet, the blue part here, from the IPv4 packet, and then forward it further on onto the native IPv6 space here. Right? This enables an IPv6 machine talking to an IPv6 machine with the middle part being IPv4. I know, allow me to illustrate. So in the scenario, we have an IPv6 space to the left and another IPv6 space to the right. I suppose we have data we want to send from A to F. Okay? Both of them, version 6, they should be able to send data to each other all right. Now the problem is this. Yeah, an IPv6 packet here will travel through the version 6 space. But as soon as it hits the version 4 space, yeah, these routers, they're old. They don't recognize the version 4 format. They will not be able to handle the packet and forward it down this way. Okay? And that is why we need tunnel. So what's being done, okay, in the tunnel is this. B being the border router, E being the border router separating the version 4 and version 6 space. It's implementing version 6 for sure, but also version 4 as well. Therefore, B and E both carry IPv6 address as well as IPv4 address. By setting up tunnel, B now actually record E's version 4 IP address. E here records B's version 4 IP address. So essentially the two ends, okay, exchange the IPv4 address. So once that's done, usually this is done offline by the network admins. Okay. Once that is done, then let's consider, okay, A here generated the packet, the blue one, and we're forwarding it towards the destination. Right? Once it hits the border router here before the IPv4 space, B, the border router, is going to do this. Encapsulate the blue packet inside a version 4 packet. In the version 4 packet, the source address is going to be B itself. Destination address is going to be the other end of the tunnel. Okay? The other end of the tunnel's IPv4 address. Now, this is an IPv4 packet, source being B, destination being E. then the IPv4 network is capable of forwarding this packet over, okay, at least to E. So E is going to receive the packet next, and being the border router, and being the other end of the tunnel, E is just going to extract the blue packet out of the red one and forward it down to the rest of the IPv6 space. And this is when F here receive the packet that is supposed to go for F. All right, now just the adoption rate. All right, so it's very short, about a minute and a half. Last slide here is not technical at all. It's to talk about the adoption of version 6. So Google once released this number. 8% of the clients worldwide accessing Google services are IPv6. Ouch, please don't. NIST is a government body there tracking all sorts of standards as well as maintaining some statistics. So NIST releases this. 30%, 33% of the US government internet is IPv6. Okay. US government is promoting strongly the move to IPv6. And to make the numbers even more pathetic, this is after 20 years of effort. Okay. Ouch. But why, right? If you think at the application layer, we have new applications rising. Okay, IG, Facebook, Netflix, other video streamings. Okay, Zoom, YouTube. Okay, newer services rising. Within each service, the protocol also get upgraded quickly, right? Changing from one version to another version. But unlike application layer changes, network layer changes, it seems very hard to do. It's not like undoable, right? We just need to upgrade the routers, upgrade the clients, reconfigure the routers, reconfigure the clients. Why is it so hard? Why is it so much easier to upgrade one app? Okay, well, hey, it's I don't know exactly why it's hard to upgrade, but what I can say is that what's on the video was in the textbook, which was published years back. Okay, the adoption rate in the textbook was about 8%, but nowadays, if you look at the upper right where we have golfer, yeah, it's now about 50%. Okay, so it's not so bad now, half. Good. And you know what, guys? We are now moving to the last chapter of chapter 4. This is what? Generalized forwarding. In fact, in chapter 4.3, that was the destination-based forwarding. And 4.4 here is the modern forwarding, the generalized forwarding. Okay. And in this first video, about 5 minutes, you will see that not only forwarding, what we match can be source address, not just destination address, but also maybe combinations of addresses or combinations of other fields in the packet header. Okay, the function, the action it takes, right? Previously, we keep saying forwarding, right? We match a entry in the forwarding table and then we forward the packet to the outgoing interface correspondingly. But in generalized forwarding or modern day data plane, the action doesn't need to be just forwarding. Okay, so there's also a variety of actions one may take. Okay, so therefore it's a little bit awkward to call this table here, previously we called forwarding table, because the action doesn't need to be just forwarding. So nowadays we call this table that we manipulate the packet coming in is called the flow table. Okay, more general. Okay, it's a little bit more like the philosophy of IPv6. We consider each stream of packets with similar characteristic of flow. All right, so each entry is called a flow entry and the table is called the flow table. Okay. Towards the end of this video, which is 5 minutes, you will see that your first example of a generalized forwarding packet traveling through the data plane of a modern router. Good, let's begin. Last section in chapter 4, generalized forwarding and SDN. So in these SDN routers, okay, the way we're doing forwarding is actually different from the traditional one, therefore we call it the generalized forwarding. In traditional routing, if you still recall, in the data plane, when packet arrives, we look at the destination IP address and we try to match destination IP address to the prefix entries in the forwarding table. If we match one, what we essentially do is to forward the packet to the link interface indicated in the entry. So in the traditional forwarding, what we're doing in terms of matching, very specific, the destination address. What we're doing as an action is simply to forward the packet further. But in SDN routers in the data plane, the matching and actions are now a lot more general. This is the architecture of the modern routing, or SDN-based routing. Now the separation of data plane and control plane, this part is actually very similar to the traditional routing. Now if you recall the overview of chapters 4, you should recognize in SDN, the control plane look very different. Instead of having routing algorithms running on each individual routers, we now run the routing algorithm centrally on one or maybe a couple powerful machines. And these machines could be slightly far away from the routers in the network. Now, what's a bit similar though between SDN routing and the traditional routing is this. After route computation, we generate tables like this. This is similar to traditional routing, right? In the control plane of the traditional routing algorithm finished computation generates forwarding table, and we install forwarding table to the data plane of the traditional router. Now, in SDN, tables are generated as well from the routing algorithm computation, and we also install these tables to the data plane of the SDN routers. You see, the control plane to data plane connection there between SDN and traditional routing, very similar. The only slight difference is this. In traditional routing, we call these the forwarding tables. But in SDN, we call them the flow tables. Okay, so each router there will be installed with these flow tables to handle packets coming in. And so the flow table, if we zoom in, it looks more like this in SDN. In traditional forwarding, we have what? Prefix, the first column, and the link interface, the second column. The actions being taken is very simple. Matching prefix, and then forward to a link interface. So what we're doing is always forwarding in the traditional routing. But in SDN, these actions could be more general, okay? Not just forwarding. So calling it a forwarding table is a bit awkward. So instead, in SDN, we call it the flow table instead. And by flow, SDN is actually referring to each of these entries, each of these rows in the table. That is also saying if packets coming into this router, where multiple of them matching a particular header combination and therefore take the same action, they belong to the same flow. So each row here is a flow. So we have a table of many flows in a sense. So what I'm showing here is also an example. Packets could come in with the headers looking like this, the destination being 0100, source IP address being 1101. Okay. Now we need to go ahead and look up the flow table in this router, and then determine it should go out on interface 2, arriving at this router next. Now in order to do that, there needs to be an entry, let's say this one here, matching the destination and source address. So in the header column of this entry, there should be specification looking like this. D equals 0100, S equal 1101. Therefore, when this packet arrives, look up, we match this entry, and therefore take the action here. Now, forwarding to interface 2, the action there should look like this. So, matching this packet to the combination of header fields and take the action. Now, in the meantime, we take the action, this thing here. For this entry, the counters, both the packet counter and the data byte counter will be added. So packet counter will be added by 1 for one packet. Data counter will be added by the size of the data here in the packet. So you see, header column here for matching purpose, last column here for action purpose, and counter here for management purpose. All right, good. So you get a rough idea. We have now a flow table and flow entries, which are more general. Now, the next video, it's gonna also run in 2 parts. In the second part, you will see 3 more examples that's not doing forwarding. Of course, there's another one doing forwarding, but it doesn't need to be just forwarding. But the first part You see in the previous video that we have matching patterns, right? There's a column that's called match, and there are different patterns that the packet can match. There's a column called action, and there are different actions, right? A packet can take. Okay, forwarding is in the example in the last video. There's a column called counter, okay, that is useful for management purpose. But you will see in this video, about 5 minutes as well, there's one more column called the priority. Okay, if you think back in chapter 4.3, when the forwarding is traditional, that we only do destination address and the matching is what? The longest prefix match. Then we don't need priority because there's always one entry we match. But now we have different patterns. Okay, they might not be mutually exclusive. There could be overlap, and it's actually difficult to come up with another rule to separate, okay, differentiate which rule exactly the packet should take action upon. Okay, you can match two entries, so we need this attribute called priority, okay, to decide eventually among all the entries that match, which one is eventually the packet follows. Okay, so this video again, 5 minutes. Let's see if you can follow. To put in simpler words, we take a combination of these header fields with specific values, and we define that as a pattern, okay, for a flow. So whenever there's a packet coming in, the SDN router is essentially determining which flow the packet belongs to, because that flow entry is going to tell the SDN router how to handle the packet. That is called the generalized forwarding. So step number 1, the most important step. For each incoming packet, take the header. Try to match the various patterns, okay, in the flow table. If there's a matching entry, go to the action column, so that's step 2, and then handle the packet that way. It could be simply to forward the packet to the next router, or drop in the packet, or modify the packet, or send the packet to the remote controller. So that is usually for debugging purpose, by the way. And step 3, increment the counter so that we track number of packets matching to the flow, number of bytes, okay, matching to the flow. Now, priority. Yeah, so this is something that we have not yet talked about, the priority column. Okay, so the flow table should have actually 4 columns instead of 3. Let me explain why we need priority there. Yeah, these patterns, okay, in the flow table, some of these patterns could be more coarse-grained. Many of the packets might match the pattern. Some might be finer-grained. Okay, few packets will match the pattern. So if we have multiple patterns that are coarse-grained, chances actually high that they overlap. Okay, therefore, for a packet incoming, that packet could potentially match to multiple patterns, multiple entries, and each entry specifies an action. So, which actions do we take then, right? So priority there, okay, is to specify which pattern carries a higher priority and which one carries less. So we could differentiate or break the tie among all the matching patterns. Which one should be taken priority? Therefore, we take the action, okay, in the prioritized entry. Okay, so priority there is to disambiguate all the matching entries. Now, in traditional forwarding, we don't need to specify a priority. Why? Traditional forwarding there is to do what? Prefix matching. We do have multiple prefixes existing in the forwarding table. So one packet could actually match to multiple prefixes. But you know what? In traditional forwarding, we are also doing the longest prefix matching. That actually breaks the tie naturally, because there's only going to be one longest prefix. Okay? Unlike in SDN, we could have multiple patterns, and the patterns are now general, right? It's not always prefix, so you cannot use the lengths to break the tie. So we have a specific priority field there to break the tie. Okay, so the forward table in a router, 4 column, and it defines how the SDN handles a packet. It defines the match and action rules. To be more concrete, let's look into 3 examples. Now, in all 3 examples, we look at the source address and the destination address header fields. Now, in example number 1, Yeah, we don't want to match the source address being 1.2 dot something. Okay, so the asterisk here meant wildcard, meaning arbitrary values for the last 2 octets. Destination address must match 3.4.5 for the first 3 octets, and then doesn't matter, okay, what the 4th octet is. Now, all packets matching this pattern will be dropped. In second example, source can be anything, but destination address needs to match 3.4 something, and then we forward all those packets to interface 2. Third entry, 10.1.2.3, as long as the source IP address is exactly this, we send the packet back to the remote controller. So 3 examples, you get a rough feeling. Now, let me come back here. I have not yet explained what OpenFlow means. Yeah, this is the data plane abstraction for SDN routers, all right. Okay, what does OpenFlow mean? Okay. OpenFlow, capital O, capital F. It's a very specific term. It is the protocol, okay, defined for communication between the data plane router to the control plane remote controller. Okay, so the remote controller installing forwarding table using the OpenFlow protocol. All right, now OpenFlow, you heard, it's the protocol communicating between the controller at the control plane to all the routers in the data plane, all these flow tables. All right. Now, let's move on to define the flow table more specifically. Okay, so this is finally a formal definition. And this video is in fact short, 2.5 minutes. With the generalized forwarding explained, now let's go back to this notion, the flow table. This is one of the most important things in SDN's data plane. Recall early slide, flow table consists of a number of columns, and you now know it should be 4 columns to be exact. There's this column priority, okay, and we just ignore that here as it's not often used in SDN anyway. The stats column is essentially the counter column in the early slide. There are 2 counters, we know, one counting bytes and one counting packets. Action column, 4 classes of actions. One can forward a packet to an outgoing interface, one can forward a packet to the remote controller. One can drop a packet as an action. One can also change the content of the packet as an action as well. So, all these, straightforward. Now, this column here, very complex. Okay. It really depends on the header fields you're using and the values you're using. So the entries, the rule column part of the entries can be very diverse. So the rule column here, yeah, in the early slide is also called a header, okay, column. The reason it's called the header column is we're using the header fields essentially to compose these rules. In the 3 examples we just walked through, we're using the source and the destination address. These are the header fields in the network layer packet header. One can use other fields in the network layer header, okay, for the rule. One can also use fields in the transport layer header, such as the source port number, destination port number, yeah, to compose the rule. One can also use the link layer header fields to compose the rule. What's even more amusing is this. These are all fields, okay, in the packet headers. One can also use fields that's outside of the packet headers. This is called the switch port. What this means is the packets, okay, coming into the router through a particular incoming port. Okay, so that's what the switch port meant, the incoming port, the incoming interface. So how we forward the packet can also depend on where they come in from. Right? So that's also why, okay, in this slide, we refrain from calling this column the header column because we do have a field that's necessary, that's not necessarily a packet header. So we call them rules in general. All right, so being able to match the packets so generally is powerful. So the next video is to give you 4 examples, and 4 of these, each one of these 4 examples is actually providing a specific function that you may have heard earlier in the course. Okay, and pay attention to this video because right after that we'll do quiz 38. That's yet another example doing special function. All right, so this video, 4 examples, about 5 minutes. Let's take a look at how diverse these rules can be. again through a number of examples. First is the destination-based forwarding. And this is essentially the traditional forwarding, where we look at the destination address. So if you have a packet, the header, the destination field says 51.6.0.8, and we forward that packet to the output port number 6. So you see here, the SDN router can actually emulate the behavior of a traditional router. And the flow table there is actually a very general form of the forwarding table. Okay. The second and the third example are there to serve security purpose, to set up firewall entries. So let's take a look at what they're doing. First one is actually trying to match the destination port number header field. So if the packet's destination port number is 22, we drop the packet. The second one is actually matching the source address header field. If the packet source is 128.119.1.1, then we also drop the packet. So you see, dropping packet definitely, okay, something that the firewall does. Now, why blocking packet going to port 22? Why blocking packet coming from a particular IP address? Allow me to explain. So port 22 is also the port number of the SSH server. So this is the server that you contact to every time you try to log into the workstation. So after you type in SSH, what do you do next? You give the username, right? And then the server is going to prompt you for password. The hackers around the world is trying to SSH into the machines around the world. Using what? A min or a root username and guessing the passwords for the root or a min. Now, if they guess the password right, then they get into the workstation and they get to play around and set things up or change things or encrypt your PA assignments and then send you ransom emails. Okay? So blocking packets to port 22 is to block any logging request to port 22. Therefore, SSH is disabled on the machines behind this firewall. Second entry there. Okay, so this is actually more to try to prevent this attack. DOS attack, denial of service attack. You see, system admins around the world, especially those who are experienced, they will go up to these websites where the system admins share IP addresses of zombie machines. So if one day a hacker hacks through the workstation and take over the workstation, 140.112.42.161 is going to be a zombie IP address. So the experienced system admin, after looking up the website displaying all these zombie IP addresses, can set up these entries with the zombie IPs here. That would actually block all the zombie incoming traffic if a higher level hacker comes in and asks all the zombie machines to issue, for example, login requests. Then our machine is going to under attack. So experienced admin setting up these entries ahead of time will prevent us from the DOS attack. And this attack is also called the SSH brute force attack. Guessing the password by repeatedly trying, that is a brute force attack. Example number 4, destination-based layer 2 forwarding. I know we have not yet talked about the link layer protocols, aka the layer 2 protocols. So this entry here could sound a bit fuzzy to you guys. Now, so let me tell you ahead of time what the purpose of the entry is. So with this entry, the SDN router is emulating the behavior of a layer 2 switch, of a Ethernet switch. I think we've seen something like that when we're talking about the subnet, right? Within a subnet, there are these interfaces that are connected, but the connection is there through a switch, through a link layer switch, or an Ethernet switch. So you see, from one machine, this network interface could have a frame passing through and coming to the link layer switch. Now, this link layer switch, we need to look at the destination address, but the link layer destination address to decide how to forward it further so that it reaches other interfaces on the same subnet. Okay, so that is the use of the switch there. So you see why. This entry here is looking at the destination address and the link layer. That is also called the MAC address, and it look very different from the IP address. So if this packet comes in matching this link layer address, then that's forwarded to output port 3. Right? So that is the idea. All right, and that takes us to quiz 38. Okay, and let me explain what quiz 38 is saying. So there we go. Okay, so we have 3 machines in a SDN network. One machine here, second machine here, a third machine here. Okay, and this machine carries this IP address. The second one here, interesting, look familiar. And this machine, look familiar. Okay, anyway, we have 3 machines in the same network. So we can use actually OpenFlow and to configure the routing entries in these 3 machines. And we have 1 entry here, okay, on this machine, and 1 entry here on this machine. So what this entry says is if we match this pattern, okay, so if 36.227.45.90 is sending something to this destination address, and the IP port number, the source port number, destination port numbers are as such, then we do these things. So these are the actions we take. We change the destination IP address to 140.122.110. We change the IP address, okay, to this guy, originally this guy. And then when the packet arrives here, yeah, because the destination is changed to 2.110, right? So it would arrive here. When the packet arrives here, it's going to match again this entry. And what the action defined in this entry is, let's change the source IP address. Interesting. So it's no longer 36.227. something. Instead, the source IP address is changed to this machine's address. Okay, while the destination address should be now 42.221. Interesting. Okay, so before we change this, the destination IP addresses of the packet was preserved, and that is actually changed, assigned to change the destination IP address. All right, and sorry. Yeah, indeed. Okay, so this is preserved, okay, and it's used as the source IP address. But the destination address is now 221, and that was actually the previous destination address. So I think one of the actions that I'm missing here, I should probably keep another field here so that I can keep this IP address. Otherwise, right, it's a little bit odd. But you know what, the OpenFlow from the controller can actually overlook this and definitely configure it this way, no problem either. Okay, so this should still work without preserving this information in the packet. And this is just to make sure that the source port number and the destination port number are matching. Okay, so in this network, with these entries specifically installed on the corresponding machines, what do you think these 2 entries are for? What is this scenario is for? All right, guys, think about it. You have only 1 minute, in fact. Okay, you know what, guys? Let's make this a take-home assignment because we have only less than 2 minutes left. Let's make this a take-home assignment. So guys, think this through and let me know what you guys think the entries are for. So the score space is, the quiz is also posted on the Discord space channel W13 quiz 38. Let's make this a take-home quiz. And with that said, we have no more time to go on and play the next video. So we'll call it a day, and tomorrow, 10:20, I will come back to check your solutions for quiz 38. Okay, with that said, I say goodbye. See you tomorrow. Okay, bye.